Hello everyone, good evening. In this live session, I am going to discuss second law of thermodynamics. Before going to the actual statement of second law of thermodynamics, let us discuss few related things. Why the second law of thermodynamics has to be used or applied or studied, and a few concepts related to second law of thermodynamics. In the very first, let us discuss limitations of first law of thermodynamics. First law of thermodynamics does not help whether the system will or will not undergo a particular change. No restriction has been imposed by the first law on the possibility of conversion of energy from one form to another. The first law does not address what portion of heat may be converted into useful form of energy and work. So these are the limitations which have led to have second law of thermodynamics. And before going to the actual statement of second law of thermodynamics, let us discuss, let us understand a few concepts which are related to construction of some devices which work on second law of thermodynamics. In that, the very first one is thermal reservoir. This thermal reservoir is a very large body of infinite capacity which will absorb or reject unlimited quantity of heat without changes in its thermodynamic coordinates. So this is a very large body which will have infinite capacity. Either it will absorb or reject unlimited quantity of heat. The examples of this thermal reservoir may be the furnace in case of thermal power station, and the combustion chamber in case of IC engines, and the atmosphere itself is a very big thermal reservoir of infinite capacity of heat, and a river can also be considered as a thermal reservoir, and even the ocean. Now there will be two types of thermal reservoirs which are heat source and heat sink. A thermal reservoir from which heat is supplied to system operating in heat engine cycle is called as source or heat source. It is a thermal reservoir which will continuously supply heat to the heat engine without any changes in its thermodynamic coordinates. Example for this thermal reservoir that supplies heat, that is heat source, may be the furnace, where combustion of the fuel produces heat, and that will be continuously supplied to heat engine to convert that heat into the desired form of output such as work. And also the another example for this heat source may be, as I already told you, this combustion chamber. In the combustion chamber of IC engine also the combustion of the fuel takes place, and that will continuously supply heat to the cylinder. The gases are expanded and that will apply the force on piston that will produce work. A thermal reservoir to which heat is rejected from the system during a cycle is called as sink or heat sink. So in this thermal reservoir, heat is absorbed from the heat engine. So here heat engine will reject some amount of heat to another reservoir that is called as heat sink. The examples for heat sink is this atmosphere. To this atmosphere, the heat rejected by the IC engines or any engines will be continuously absorbed without appreciable change in its thermodynamic coordinates. And even river will absorb heat from the heat engine, external combustion heat engines, that is in case of thermal power plants, heat is rejected from the condenser to condense the vapor to liquid form. So that is also rejected to this river, and sometimes heat is rejected to ocean when the thermal power station is located near the sea, near the sea. So these are a few examples for heat sink. And after that, let us discuss how exactly heat engine work. This heat engine continuously receives net work, and that will produce net work output in a cycle. This will operate in a cycle. And if you have any questions, please post in the chat box so that I can answer whenever it is required. Okay. I was telling about heat engine. So this heat engine will receive net heat and produces net work output. So that is the purpose of heat engine. To understand how exactly this heat engine works, let us consider vapor power cycle that is applied in thermal power station. Let us start understanding of this vapor power cycle from one of its very important component, that is boiler. This boiler receives Q1 amount of heat from furnace where combustion of the fuel takes place. Here furnace is heat source, and that will supply continuously heat to the water, that is working substance in case of vapor power cycle, that is flowing in the boiler tubes. At the outlet of the boiler, there will be steam which is at high pressure and high temperature. That high pressure, high temperature steam is supplied to a turbine, where that steam expands and works and does work upon the turbine blades. So that will produce work output, and the low pressure, sometimes it may be dry saturated or wet steam comes out of the turbine, and that enters condenser. Here condenser rejects Q2 amount of heat to atmosphere to get condensed from vapor to liquid phase, and the state of the working substance water at the exit of the condenser is liquid, and that liquid water will be pumped back to boiler using the pump that consumes WP amount of work, and that will supply that will pump the working substance back to the boiler. This is how heat engine operates in a cycle, and that receives net heat input, that is Q net is equal to Q1 minus Q2. Here Q1 is positive because heat is added to the system, whereas Q2 is negative because here Q2 is rejected from the system to the surroundings. So it has already been discussed that the sign convention of heat and work, and similarly, if we take the net work produced by this heat engine cycle, that W net is WT minus WP. Here WT is turbine work, that is work done by the system is taken as positive, and work done on the system is taken as negative. So here WT, that is turbine work, is work done by the system, so that is W plus WT, and WP is done on the system, so it is negative. Then according to first law of thermodynamics, sigma Q cycle is equal to sigma W cycle. Then Q net is equal to W net. So that is the heat engine. Now let us before understanding the concept of this heat engine, let us have another type of heat engine, that is IC engine. In case of IC engine, the working substance is air. That air receives heat when the fuel is the fuel gets burnt in the case in combustion chamber, and that combustion takes place when that working substance air is compressed when the piston is at top dead center at the end of the compression stroke and at the beginning of the expansion stroke, and that combustion, that heat released by that combustion will apply force on the piston, so that piston moves, and that will produce work, and some amount of heat is rejected to atmosphere. So here the net heat that is supplied is Q1 minus Q2, and similarly the net work is the work that is produced by the movement of the piston, and minus that is that work absorbed by the piston to move back to its initial position, or to top dead center, or to the inner dead center. So that is the concept of heat engine in case of IC engines. And in general, this heat engine can be understood in this way, that is heat engine will always receive Q1 amount of heat from heat source, and it will convert some amount of this heat into work, and rejects remaining amount of heat to heat sink. So this is how the heat engine works in general, either in case of vapor power cycle, or in IC engine, or in any type of engine that converts heat into work. So that is what exactly this is how exactly it works. And here temperature of the source is always greater than temperature of the sink, so heat spontaneously flows from a reservoir at higher temperature to a reservoir at lower temperature. So that spontaneously takes place, and the performance of heat engine can be obtained or studied by understanding the efficiency of heat engine. That is, efficiency is the work output divided by heat input. Here in this case, work output is this WT. So WT divided by heat input is Q1. So then in the next step, that is WT is equal to Q1 minus Q2. See, if we apply energy balance at this heat engine, sum of all heat or work that is entering is equal to sum of all energies which are going out. Sum of all energy entering is equal to sum of all energy leaving. So then Q1 is equal to Q2 plus WT. Here we need WT, so this WT will be Q1 minus Q2. So that is what exactly it is written here. Then efficiency will be Q1 minus Q2 divided by Q1, or this can also be written as 1 minus Q2 by Q1. So this is the efficiency for heat engine. And okay, I am getting a few questions like this from Mr. Deepak. I got a very basic question, that is thermodynamics. that was discussed very long ago. Thermodynamics is a sense of heat transfer. Thermodynamics sense of heat transfer, in which we will study the conversion of energy from one form to another form. Here we will usually study heat and work interactions. Simply, it is a science of energy transfer, and based on the observation of the common experience, thermodynamic laws have been formulated, and these laws are applied in almost all fields of energy technology, such as in IC engines, refrigeration, air conditioning. In general, it is a science of energy transfer. Here, this thermodynamics kind from two words. Therm means heat and dynamics means power. After that, I got another question from the same Mr. Deepak, that what exactly condenser means. Condenser, you will study that condenser in detail in your vapor power cycles. That is the last chapter in this thermodynamics. The purpose of condenser is to convert the working substance, that is water, in the vapor phase. Vapor phase means it is in the gaseous phase, to the liquid phase. So usually water is called as steam in the gaseous state, and in the liquid state it is simply it is called as water. So it is the conversion of vapor to liquid water is actually called as condensation, and that condensation takes place in a device called condenser. This process takes place at constant temperature. You will understand better when I start discussing about pure substance in the coming live sessions. During that, I will explain in detail about that condensation and what exactly that condenser and why should that be condensed. I will discuss that one during the vapor power cycles. And after that, once again from Mr. Deepak, I am getting the question, internal energy wares are in the first law of thermodynamics. That was also discussed during the discussion on first law of thermodynamics. What happens in case of when heat is added to a system where it will produce some amount of work, and the remaining heat is stored in the system itself, and that stored energy is called as internal energy. For example, if we supply some 20 kilojoules of heat to a system, and if some 18 kilojoules of work is produced by that system, then the remaining 2 kilojoules of heat is stored inside the system, and that energy, that is stored energy in the system, is called as internal energy. And you can understand better when you see my videos on first law of thermodynamics. If there are any questions, please let me know. If more and more interactions are there, it will be definitely motivation to answer better and also to have the successful sessions. So I hope the concept of heat engine is cleared. If it is not cleared, and if you have any questions, please let me know. And after that, after the concept of heat engine, now the refrigerator. You people know about this refrigerator. Almost all domestic purpose this refrigerator is used. In almost all house will have this refrigerator. It is actually fridge. This refrigerator maintains the space at a temperature less than the temperature of the surroundings. So let us see how exactly this refrigerator works and how it is related to this energy transfer. So for that I will start this refrigerator with one very important component that is usually called as the heart of the refrigerator, that is evaporator. So earlier I told you about condenser. Here it is evaporator. What exactly evaporator does? This evaporator is a device. Here working substance that is used in case of this refrigerator is refrigerant, that is changed from its liquid phase to vapor phase, that is gaseous phase, by receiving Q2 amount of heat from the surroundings. So when heat is added to the working substance, its phase changes from liquid to vapor, but whereas when heat is rejected from the vapor, that is converted into liquid. You will understand those things better in the coming concepts when we are going to discuss in deep about the phase transformation from liquid to vapor, vapor to liquid, solid to liquid, liquid to solid. You will understand those things better. But in this evaporator, by receiving heat, Q2 amount of heat from the surroundings, here phase transformation takes place from liquid to vapor. So here temperature of the working substance refrigerant is less than the temperature of the surroundings. So heat transfer takes place from surroundings to that working substance. So the temperature of the surroundings becomes reduced. So that is the desired effect in case of refrigerator, where we have to maintain the temperature of that space less than the surroundings. And also what is the amount of heat that is to be removed from that refrigerated space is equal to the amount of heat that is leaked from its surroundings, that is from the external to that refrigerated space to that refrigerator, that refrigerated space is the heat that is to be continuously removed from that refrigerated space, and that will be understood better in the coming discussions. So here the evaporator will receive Q2 amount of heat, so that the refrigerant changes its phase from liquid to vapor. Then that vapor is supplied to a compressor. Here by receiving WC amount of work, that is the work that is absorbed by a compressor, and this compressor will compress that vapor, and that will be sent to once again condenser. Here this condenser will reject Q1 amount of heat to the surroundings, and then condensation takes place once again here, and the exit of the condenser is liquid refrigerant, and that liquid refrigerant enters the expansion valve, where it gets expanded, and when it is expanded, its temperature decreases, so that low temperature refrigerant enters the evaporator. That is how the heat from the refrigerated space is removed and rejected to the atmosphere. That is how it takes place. So in case of refrigerator, this refrigerator will absorb heat from a low temperature refrigerated space and reject to high temperature surroundings. That is the purpose of the refrigerator. In doing so, this refrigerator receives WC amount of work. That is very important. So that is how this refrigerator works. And this refrigerator is also called as reversed heat engine because it works reverse to that heat engine. I will tell you how exactly it is reversed heat engine, that is refrigerator. So this refrigerator receives Q2 amount of heat from body which is at a temperature of T2, or body that is to be maintained at a temperature less than the surroundings, and that will reject Q1 amount of heat to the atmosphere which is a temperature higher than the temperature of the body, by receiving WC amount of work. That is very important. So here those directions are reversed. So when all the directions of the heat engine are reversed, that becomes reversed heat engine, that is called as refrigerator. So here one very important thing is the temperature T2 is less than that of the temperature T1. So here so always heat transfer takes place from a body at lower temperature to atmosphere which is at a higher temperature than the body. Then some external work has to be used. Okay, so that is about refrigerator. So in case of refrigerator, so the heat transfer takes place from a body at lower temperature to an atmosphere which is at a high temperature by receiving work. But as you all know, it spontaneously flows from body at higher temperature to body at lower temperature. That happens in case of heat engines. In doing so, that will produce work also. So performance of this refrigerator can be done using the term coefficient of performance, that is more popularly called as COP of refrigerator. So that is defined as desired effect divided by work input. That is what exactly. Here desired effect is this one, that is to have some effect. What is the amount of heat that is to be removed from the refrigerated space or a body to maintain, that is the desired effect, divided by work input is this WC, that is supplied to compressor. Then this will be WC is equal to Q1 minus Q2, and this can once again be obtained by doing energy balance at this refrigerator. So all the energies entering, sum of all the energies entering is equal to sum of all the energies leaving. So here this will be Q2 plus WC is equal to Q1. To have this WC, then this will be Q1 minus Q2. So that is how WC comes. Then the COP of refrigerator can be written as Q2 divided by Q1 minus Q2. So this is the COP, coefficient of performance of refrigerator. To find the performance of refrigerator, we can use this formula, that is Q2 divided by Q1 minus Q2. After studying this refrigerator, let us discuss what exactly this heat pump. The concept of heat pump is same as refrigerator, but the desired effect is not the lower temperature, but the desired effect is the higher temperature body. I will tell you in a very simple way. what exactly that this heat pump does. See, this heat pump receives Q2 amount of heat from the atmosphere, and that will continuously supplies heat to body which is at a temperature T1, which is more than the temperature of the atmosphere, by receiving WC amount of work. Everything is same, that is Q1, Q2, WC, all are same as the refrigerator, Directions are also same as the refrigerator, but in this place previously it was body or refrigerated space that is to be maintained at a temperature less than the surroundings, but in this case it is atmosphere. But whereas in case of refrigerator, this place was atmosphere, but in this case it is heat pump. So what is the purpose of heat pump? To maintain the temperature of the space or body more than the surroundings by receiving heat from surroundings. So this is usually applied in places where the comfortable temperature is very less, or the we can say the temperature of the that environment or temperature of the temperature of the place is very less. So in the cold regions, room has to be maintained at a temperature higher than the temperature of the surroundings. So in that case, this heat pump will receive heat from the surroundings and will pump to the room or to the body that has to be maintained at a temperature higher than the temperature of the surroundings. So that is the difference between the refrigerator and heat pump. So in case of refrigerator, the desired effect or desired place is the temperature which has to be maintained at a temperature less than the surroundings, but whereas in case of this heat pump, the body or the space has to be maintained at a temperature higher than the temperature of the surroundings by receiving heat from the surroundings itself. So here as usual, once again, temperature of the atmosphere, that is temperature T2, is less than the body temperature T1. Here as I already told you, heat is transferred from lower temperature system to higher temperature system by consuming once again WC amount of work. Now let us see whether the performance of refrigerator and performance of heat pump same or different. Let's see. Once again, coefficient of performance of heat pump definition is also same as the definition of the refrigerator, but the only difference is the desired effect is this space by where that receives the heat of Q1. So desired effect in this case is Q1. So once again, work input is this WC itself. Then in the next step, that means here desired effect is Q1, means to maintain the temperature of the body more than the temperature of the surroundings, we should supply heat to that body or space at which that will leak the heat to atmosphere. So that is what exactly the desired effect mean by. So this COP of heat pump will be Q1 divided by WC, and as usual WC is once again Q1 minus Q2. This is obtained by applying this heat balance at this heat pump. Then all the energy entering is equal to all the energy leaving. Then we will get Q2 plus WC is equal to Q1. Then this WC will be Q1 minus Q2. When we bring this Q2 to the right hand side, that will be Q1 minus Q2. Then if we substitute thus the WC to this heat pump expression, we will have COP of heat pump will be Q1 divided by Q1 minus Q2. You are observing the COP definition of heat pump and refrigerator both are same, but when we proceed further, the expressions are not same. COP of refrigerator was Q2 divided by Q1 minus Q2, but whereas COP of this heat pump is Q1 divided by Q1 minus Q2. I will explain the difference between efficiency and coefficient of performance after completing this heat pump. I am getting that question from once again Mr. Deepak. I am very happy that for this interaction. Here to proceed further, we will have like this. I will add and subtract Q2 to this numerator. So this will be Q1 plus Q2 minus Q2 divided by Q1 minus Q2. So that will not make any difference if we add and subtract this Q2 to this expression. Then we will have arrangement like this, Q1 minus Q2 plus Q2 divided by Q1 minus Q2. We have just rearranged, that's all. Then in the next step we can write down like this, Q1 minus Q2 divided by Q1 minus Q2 plus Q2 divided by this Q1 minus Q2. So separating these plus things with fractions, and after that this becomes 1. So this will be 1 plus, this is once again Q2 divided by Q1 minus Q2 is COP of refrigerator. So COP of heat pump is 1 plus COP of refrigerator. So that is about COP of this refrigerator. Okay, at this very point itself, I would like to share the difference between efficiency and COP. Here efficiency will be related to heat engine, where that will convert heat energy into work output. So in this case, efficiency will give what portion of heat is converted into work. So that is efficiency. So that efficiency will be work output divided by heat input is efficiency, right? So that is that one. And whereas that efficiency will be to that heat engine, as I already told you, that converts heat into work. But whereas that refrigerator and heat pump will decide at what rate they will absorb heat from low temperature reservoir and then reject what amount of heat to high temperature reservoir is the performance of a refrigerator. So this coefficient of performance is, as I already told you, it is desired effect divided by work input. So if we take the example of refrigerator, that is once again at what rate heat has to be removed from the refrigerated space is the coefficient of performance by absorbing WC amount of work, that is the COP of refrigerator. Whereas the COP of heat pump is here at rate this heat pump will supply heat to the body that has to be maintained at a temperature higher than the temperature of the surroundings by receiving WC amount of work, that is the coefficient of performance of refrigerator and heat pump. I hope you have understood this difference between efficiency and this COP of refrigerator and heat pump. Definitely COP of refrigerator and heat pump slightly different, as the refrigerator will absorb heat from the refrigerated space. So it is at what rate that refrigerator will absorb heat by consuming WC amount of work, that is COP of refrigerator. But whereas COP of heat pump is at what rate it can supply heat to the body or to the space that has to be maintained at a temperature higher than the surroundings by consuming WC amount of work. So that is the difference between efficiency and heat pump. If you have any questions, please post, so that I'm very happy to clear. And thank you for your response, Deepak, Mr. Deepak, and you are welcome for your thanks. I hope you are cleared. Okay, and after that let us proceed further. Okay, what is the percentage of efficiency in refrigerator and heat pump? No, there is no question of percentage of efficiency in refrigerator heat pump. There is no concept of efficiency in case of refrigerator and heat pump. There is no concept of coefficient of performance in heat engine. So usually we will have percentage of efficiency in case of heat engines. Usually thermal efficiency of heat engine may be around 30%. Sometimes with advanced technology that has been increased so to some 35 to 40%. So usually we will call efficiency, we will mention efficiency with percentage. But whereas COP we will not mention with percentage. We will have some numbers like COP of 5, COP of 3, COP of 2, like that. You will understand better while solving the problems on this heat engine and heat pump. I will take up those problems in the next live session, which is on next Friday. If it is cleared, it's okay. Otherwise, let me know if you want to still elaborated answer. No, it does not have any unit. Sorry, I forgot to mention that one. Question from Mr. Deepak once again, that what is the unit of COP? So COP and efficiency will not have any units because see here the unit of this heat and unit of work are both same. If they are at rate, then they will be you have a unit of watt and watt. Watt in the numerator and watt in the denominator get cancelled, or joule in the numerator and joule in the denominator get cancelled. So COP and efficiency both will not have any unit. So after that, any more questions? I am really happy to answer the questions. COP does not have a percentage. I don't think it is a unit, but sometimes we will not mention the efficiency with percentage. We will have 3 efficiency, right? You will understand that one while solving the problems. If we have 0.3 efficiency, means that is 30% actually. Percentage is not a unit, I can say. Mr. Deepak asking the question, but efficiency has a percent as unit, but a percent is not unit. It is sometimes, as I told you, efficiency is mentioned with like 0.3, 0.4, 0.5. You will understand how exactly that 0.3 like that also. Any other questions? Please, if any others have any questions, please let me know. I think it is cleared, Mr. Deepak. Okay, let us proceed further. Let us see. Yes, I already told. I think you are not. See, in a very simple term, I will tell you. Huh? See, efficiency is with heat engine. Efficiency. I will get back to that slide. Wait for a minute. See, concept of this heat engine. Okay. See, this efficiency is defined as work output divided by heat input. So, here efficiency means what portion of energy is converted into work. That is, what portion of heat that is supplied here Q1 is converted into work is efficiency. So, work output divided by heat input is efficiency. But whereas, see, this is WT divided by Q1. But when we go to that COP, heat will be in the numerator, work will be in the denominator. So, COP is, as I already told you, at what rate refrigerator will absorb heat from the refrigerated space by consuming WC amount of work is the COP, right? It is exactly opposite to the COP is exactly opposite to this efficiency. While studying, you can understand that one better, and also while solving the problems, you will be convinced, I think. If you this is here, it is work output divided by heat input. I will show the concept of COP. See, when you come to see here, it is desired effect means here we will have this Q2. See, this Q2 divided by WC, but whereas efficiency W divided by heat supplied. I think it is cleared. I am happy to see that message. Yes, now it is cleared. If there are any more questions, I am happy to have that one. Okay. After this, I am going to discuss the actual statement of this it is a throttling process. The process involved in expansion valve is throttling process. It is ice enthalpic process. That's what exactly here the enthalpy will not change. It is an ice enthalpic process. The question from Mr. Deepak is, what is the process involved in expansion valve? So it is an ice enthalpic process. Okay, now I am going to explain, I am going to discuss the actual statement of the second law of thermodynamics. That very first statement is Kelvin-Planck statement. It is related to it is with reference to, it is related to heat engine. See, it is impossible to construct a heat engine that receives Q1 amount of heat from heat source and converts that heat completely into work without rejecting heat to heat sink. It is impossible. Here Q2 is 0. The net work output from this heat engine is equal to Q1, and then efficiency is 1 or it is 100%. So this is impossible. This is impossible. But the heat engine, that Kelvin Planck statement follows this one, that is heat engine receives Q1 amount of heat from heat source, thermal reservoir heat source, and then converts some portion of this heat into work, and then rejects Q2 amount of heat to low temperature thermal reservoir, that is also called as heat sink. So here temperature of the heat source is greater than the temperature of the heat sink. So this is the statement of Kelvin Planck statement of second law of thermodynamics, and this arrangement is possible. Yes, this arrangement is possible. Yes, I am getting very interesting questions from Mr. Deepak. I am very happy. Actually, I will explain isenthalpic process afterwards. Before that, I am getting this question that in Kelvin Planck statement, internal energy is 0. Am I right, sir? But that internal energy concept will not come in the second law of thermodynamics. We will come across another property that is called as entropy in case of this heat engines and all those things. But that internal energy concept comes only in first law of thermodynamics, and that will have a concept of internal energy, that is the property of the system in case of first law. But here we will not come across that internal energy in the second law. Second law will lead to the definition of entropy. I will tell you after that. Yes, I am getting more and more questions like PMM2. Yes, I will tell you PMM2 afterwards. After this, I am going there. I will tell you. I hope that is cleared. Internal energy 0 is cleared. Yes. I will explain that one. In the first figure, you are telling it is PMM2. Very good. But I will explain that one once again in the next slide. Yes, you already told that first impossible sketch is PMM2. You are absolutely right. That is PMM2 means perpetual motion machine of kind 2. After understanding this Kelvin Planck statement, I will have this Clausius statement. Then I will go to the PMM2. I am getting that question from all-rounder father. Right, Clausius statement. I will quickly discuss this Clausius statement. Here it is impossible to construct a device that will receive Q2 amount of heat from body at temperature T2 and rejects Q1 amount of heat to atmosphere, which is at a temperature higher than the body, without receiving any work. Here this WC is 0, right? Without receiving any work, that is supplying heat to high temperature reservoir from the low temperature body. So this is impossible. Here temperature T2 is less than T1. This arrangement is impossible. Then what is possible? So here refrigerator receives Q2 amount of heat from low temperature reservoir and rejects Q1 amount of heat to high temperature reservoir by receiving WC amount of work, and here temperature T2 is less than T1. This arrangement is possible. This follows the Clausius statement of the second law of thermodynamics. So Kelvin Planck statement is related to heat engine, whereas the Clausius statement is related to refrigerator. Now I will discuss what exactly this perpetual motion machine of kind 2, or simply it is called as PMM2. So this is the violation of second law of thermodynamics, that is Kelvin Planck statement. Here this heat engine receives Q1 amount of heat from high temperature thermal reservoir or heat source, and that will convert complete heat into work without rejecting heat to low temperature reservoir or heat sink. And here Q2, that is heat rejected to heat sink, is 0, and net work produced is equal to heat that is supplied to that heat engine, and efficiency of this perpetual motion machine of kind 2 is 1, or it is 100%, right? And such a fictitious machine does not exist. It is called as a perpetual motion machine of kind 2. So that is about some of the concepts of the second law of thermodynamics. And this perpetual motion machine does not exist, that is another thing. Actually, why internal energy is not considered? Actually, in case of this heat engines, internal energy means energy stored in the system, but here energy will not be stored in the system. Energy is rejected to the sink or atmosphere. That is why we will not consider internal energy in case of Kelvin-Planck statement. Mr. Deepak asking the question, why internal energy is not considered in the Kelvin-Planck statement? Because as I told you, internal energy means energy stored in the system. That comes only in the first law of thermodynamics, but whereas in the Kelvin-Planck statement, the remaining amount of heat is rejected to heat sink, so we will not have internal energy concept in case of this what is that Kelvin-Planck statement. Yes, really good question, very good interaction. I feel very happy to answer these your questions, your queries. There is no concept of internal energy, my dear friend Mr. Deepak. It will not be zero, it will not be zero. There is no concept of internal energy in case of this second law of thermodynamics, that is Kelvin-Planck statement. You will not come across internal energy concept in the second law itself. Then there is no question of zero or something else. Yes. Yes, you cannot relate that internal energy to this second law of thermodynamics. First law will come out with internal energy, property internal energy, but whereas, as I already told you, this second law will come out with property entropy that is equivalent to internal energy in case of first law of thermodynamics. I hope it is clear. Thank you. Thank you. I hope it is clear. Very good. I will stop the concepts here and I will continue in the next live session. If you have any questions, please let me know. I will be there for another 2 minutes. Questions are welcome. Actually, Mr. Deepak asked another one question, that is, what is ice enthalpy? Ice enthalpy means enthalpy before throttling and enthalpy after throttling are same. That is ice enthalpic process. Isothermal, as I told you, isothermal, it is constant temperature process. I told you isentropic, constant entropy process. Like this, it is ice enthalpic process. That is, enthalpy before throttling is equal to enthalpy after throttling. That is ice enthalpic process. That means energy will not be changed before and after the process in case of any fluid. That is what exactly ice enthalpic mean. I hope it is clear. Ice enthalpic also. Yes, I am really inspired by the questions people are really asking. Enthalpy is actually energy possessed by the flowing fluid. Here, if I take the example of boiler, boiler receives heat and that is supplied to the working substance that is flowing inside the boiler. When heat is supplied, its enthalpy increases. So that enthalpy concept comes to flowing substances, flowing working substances. But whereas entropy is the energy that is not available for the useful work is entropy, and you will understand that better in the coming sessions. We will have a separate chapter called entropy in the coming. I will explain that one in detail, and you will understand this enthalpy, entropy in detail while solving the problems on pure substance as well as problems on vapor power cycle. Even if I tell in detail also, it may be difficult for you to understand those two concepts. While solving the problems, you will understand better. Any other questions? Please, if you have any other questions, please tell me. Please ask me. I think it is very informative, learn and interaction, I can say. Yes, I hope it is clear. Thank you. You are welcome, Mr. Deepak. Okay, I'll wait for another 2 minutes. Next session is on next Friday. Every Friday at 8 o'clock I am coming live up until December last week. Until December last week I am coming live every Friday from 8 to 9. I am answering the question to Mr. Deepak. Is asking when is the next session, sir? I am coming live on all the Fridays up to December last week from 8 to 9. Thank you very much. Namaste, Mr. Deepak. Namaste. Okay, with that I will end this session. Let us join. Hopefully, let us join in the next session. Stay home, stay safe. Thank you very much. Good night.